So the aim of this lab experiment is to filter out the respiratory as well as the PPG signal from a combination of the both of them using the fast Fourier transform, and also find the respiration rate using the fast Fourier transform via the Arduino platform as well as Matlab. So what is the fast Fourier transform? Well, the fast Fourier transform is just a computationally efficient way to calculate the discrete Fourier transform using a recursive relation. The basic concept is you split the time domain signal into odd and even sequences and then compute the Fourier transform, the discrete Fourier transform of those odd and even sequences. And once you do that, you get a recursive relation. That is x of k is equal to g of k plus w k n h of k. Now, both this g of k and h of k can be further broken down into another recursive relation. An example of that can be g of k is equal to p of k plus w k n by 2, because the length of the sequence is reduced to half n of k, and the same thing can be done for h of k. So as you can see, we have found a recursive relation due to which the complexity reduces, as it is just a simple divide and conquer algorithm. Now if you compute the discrete Fourier transform using naive methods, you are going to get a complexity of an order of n square, whereas if you calculate it using FFT, the complexity will be of the order of n log n, n log n to the base 2 basically. And that is very useful when you have to compute sequences of very large lengths, and also when you are actually splitting down the signal into smaller signals, and then if you want to get the results instantaneously, it makes more sense to use a faster algorithm. Now, what is the main aim of our experiment? So once the main aim of our experiment is just basically you get the magnitude, you get the magnitude as well as phase spectra in the frequency domain, and filter out parts of this magnitude and phase spectra that are essential to us and leave out all the rest. So that is the basic concept of what we're trying to do. So what I mean by that is, suppose we want to filter out the respiratory signal. We know that the frequencies in real life that the respiratory signal corresponds to is around 0.05 hertz to 0.5 hertz. So corresponding to this, we have corresponding to this 0.05 as well as 0.5 hertz, we have certain indices that we can obtain that are present in that are as indices in the DFT computation. So what I mean by that is, you don't get a direct frequency correlation, you get a frequency correlation to an index. The reason that follows is because we use a sampling rate. So we have a relation that is f, which is the frequency, divided by the sampling frequency, is equal to the index divided by the length of the signal. This relation holds true because our entire frequency has to lie between -1/2 and 1/2. So if you want to find out this particular frequency, if you want to find out the index, you have to multiply the frequency, that is something like between 0.05 to 0.5 hertz in case of a respiratory signal, divide that by the sampling rate, and multiply it by the length of the signal that we want to compute the DFT for. So once the unnecessary components are filtered out, you get a magnitude as well as phase spectra. And once you have the magnitude and phase spectra, you can use the inverse Fourier transform to get back the original signal in the time domain. So therefore, you can once you get the original signal back in the time domain, you have the respiratory signal, and now since the other signal is no longer necessary, you have got what you want. The same thing can be done for the PPG signal. You can remove the frequency as well as phase components of the respiratory signal, and once you compute the inverse Fourier transform, you will get back the time domain signal that corresponds to the PPG signal. Now once you have done all of this, you can also get the pulse rate. So how do you get the pulse rate? Well, the pulse rate can be computed as follows. Once you have got the magnitude and phase spectra of either the PPG or the respiratory signal, you can look at the index that corresponds to the maximum value of the magnitude of that particular index. So what I mean by that is, when you take the magnitude of your if you take the magnitude of your DFT, you get certain magnitude that corresponds to certain indices, right? And if you take the maxima of that, if over all those values, if you take the maxima, that will correspond to the dominant frequency. and the index that corresponds to the dominant frequency is assumed to be the inherent frequency of the entire signal. So the pulse rate can be calculated as follows, which is 60 into fs into the max index that corresponds to the magnitude divided by the length of signal. Again, this relation is again derived from the fact that f by fs is equal to index by length of signal, and it is multiplied by 60 just so that it is computed in beats per minute. So now the Arduino code uses a library which is the Arduino FFT library, which is got from an open source repo. Now, the funny thing of this library is all the computations are in place, so we have to define a lot of variables here, so a lot of arrays here. And initially, what we do is we have two arrays called vreal and vimaginary. Those are the arrays you feed for computing the fast Fourier transform. So initially, you just pass it through a moving average filter, and once you pass it through a moving average filter, sorry, once you pass it through a moving average filter, you remove all those frequency components, and you want to make it a zero mean signal, right? So the main logic for making it a zero mean signal is so that there are no DC components present, so that you don't get a very high magnitude value at the frequency of 0. And we have defined the array to be of size 512. This is because the FFT library takes only sequences that are of a power 2 power x. So you have to take the 2 power x value that is greater than the length of your data, and the nearest one is 512. So that is what we have done before. And to compute the FFT, first you use a windowing technique. You weight the data, and once you use this windowing technique, you just use this particular line, that is, you take the real part and the imaginary part. In our case, we have defined the imaginary part to be 0 and our samples are 512, and you just say FFT forward, and then computes the forward that just computes your FFT. Now to filter it out, this index can be computed using the same formula, that is index by length of signal is equal to f by fs, and since the max frequency that the respiration is going to go to is 0.5, we can find out the index. And once this index is known, since the frequency spectra is symmetric across n by 2, the magnitude of the frequency spectra is symmetric across n by 2, we have to filter out the signal from both ends. So if this variable is less than the index value, we'll make the PPG real and the PPG imaginary 0, for the sole sake that the assumption is the PPG signal does not exist in those frequencies, and only the respiratory signal exists in those frequencies. Similarly, in those indices where this condition is not satisfied, we make the respiratory as well as we make the respiratory signal 0, and the PPG signal should exist at those indices. And so what we can essentially think of is a parallel that we just use a window where we pick out certain frequencies that we think correspond to the frequency of the actual signal, and then use the inverse Fourier transform for that. So now we want to find out the index that corresponds to the peak, right? So we just take the magnitude response and we find out the maxima between that and the index. Or you can just take, and the reason I compute only till the index value is because that is the only place where, since that is the only place where a respiratory signal is defined for. After that, all of them are a bunch of zeros, and until it starts repeating again from the max length of the signal minus the index value. So this basic code just computes the index of the maximum value, and we have to print the frequency plots, right? So frequency plots can be printed because you have the data of the no, but in this case, this vreal doesn't correspond to the real part of the signal. Since all the computations are happening in place, this vreal actually corresponds to the real part of the Fourier transform, and the imaginary part corresponds to the imaginary part of the Fourier transform. So so this just calculates magnitude response, and this calculates magnitude response for the PPG signal. Sorry. and this calculates the magnitude response for the respiratory signal. Now we end up dividing this by 10,000 just so that the graph looks better. And to print the time plots, we just use the inverse Fourier transform, which is computed as follows. You just use the FFT reverse instead of FFT forward. And once that is done, you convert that into magnitude, so that the so that you don't have to sit and do something like this all over again. And once you do complex to magnitude, all you have to do is just print this value. You don't have to do this. You can just, I could have just printed VDL, but I guess I was lazy and I just copied this thing back here. And once that is done, you get these plots. So you can see that the filtration has happened. This green thing corresponds to the DFT of the PPG signal, and that exists only from here till here, and everywhere else it's 0. The blue represents the FFT or the DFT of the original signal, as you can see, the blue exists through the entire frequency duration, and the red corresponds to the PPG signal. Hence, you can see that at the initial part it doesn't exist, but exists later on. And the reconstructed signals are as follows. These signals look a bit messy because these have been displayed on the same window, and hence, due to the differences in magnitudes, the signal look clumped up together and looked like noise. However, these are the actual signals as well. And the reason that we can corroborate this is we have run the same thing through a Matlab code, and the breathing frequency that we have, breathing rate that we have got through the Matlab code and Arduino are lie within the range that we want. Hence, this waveform is true. The only thing is there are issues such as I have computed a lot of things using such kind of things, which lead to some truncation errors. So there is an error between the computation using Matlab as well as Arduino, and that we'll be able to see through the table later on. So the Matlab code is pretty easy actually. We do the same process as we have done before, but the great thing of using Matlab is you can calculate the FFT just using this, and you can filter it out just using matrix slicing that we have done here. You just take the filter start index plus 1 till the length of the entire signal minus the filter and make that 0. That will give you the respiratory signal. And if you calculate the inverse Fourier transform, we get the respiratory signal in the time domain. The same thing can be done by the PPG FFT, where since you have the FFT, once you subtract the respiratory FFT, you're going to get back the PPG FFT. So once that is done, all you have to do is calculate the inverse Fourier transform of the PPG FFT to get the PPG. Now, the respiration rate is pretty simple. You just calculate the maximum, the index of the maximum value that lies between index value 2 and the filter index plus 1. So we have taken an index value of 2 in this case because in this particular code we have not computed any zero mean. So the signal has, we have not subtracted any, the signal is not zero mean, and hence it has a DC component. So if we start from 1, we get the maxima to be 1 because the DC component is very high. Hence we have started from the value of 2. And again, you can calculate the respiration rate using the same formula as we have done before, and this is just for plotting. And the plots are as follows. And as you can see, the filtration has been done properly. You're getting back the respiratory signal. We're getting back the FFT of respiration, the FFT of PPG, the PPG data, and the original data. So all of these plots are fine. And the breathing rates are computed using Matlab as 16 and Arduino using using Arduino we're getting it as 25.6 in both of them in BPM. So both of them lie within the expected range, that is 0 to 30. I guess the difference in these two occur because I have used naive methods such as square root and addition and all of that, and these are bound to have some truncation error because Arduino is not a platform that computes more than certain bit sizes. So because this is very sensitive to all this, there is a difference. However, the error is not that much because the original signal was supposed to have a BPM of around 20 to 22. So the error is not that much, and considering that we are not trying to find out if there is any issue with the person's breathing rate, such margins of error are allowable. So I think that is the end of my video. Thank you for your time.